Imagine taking something that's, been sitting around for decades, stuff deemed way too hot to handle, and turning it into a lifeline for cancer patients.
It sounds like science fiction almost.
Doesn't it? But that's the incredible story we're doing a deep dive into today, how this company, Terrapower, is doing exactly that with a very specific radioactive isotope.
Right.
So our mission here is to really get our heads around the science, the fascinating science, and the potentially groundbreaking implications of this whole new approach to cancer treatment.
And it starts really with a bit of history.
Mm.
Because, most reactors we think about use uranium-235, maybe plutonium-239.
Standard stuff.
Yeah, the standard stuff. But back in the mid-20th century, the U.S. was looking at another option, uranium-233. It actually showed, well, quite a bit of promise for power, but also for weapons.
Okay, so uranium-233, the next big thing, maybe. What happened? Why didn't it take off?
Well, the main hurdle was just how radioactive it was.
Huh.
I mean, significantly more hot than the same amount of U-235.
So difficult to work with.
Incredibly difficult to handle safely, to process, and, a big one to keep secure. So ultimately, the U.S. decided, nah, let's not pursue this. And they basically stockpiled what they had. It's been sitting at Oak Ridge National Laboratory for years.
Still radioactive, still needing careful management.
Oh, yeah. And for a long time, the main question was just, how do we get rid of this safely? How do we dispose of it?
Okay, but then things take a twist. This company, Terrapower, founded by Bill Gates back in 2006, they look at this stuff everyone else sees as dangerous waste.
And they see potential, not just waste, but a resource.
Specifically for nuclear medicine, like actual cancer treatment.
Exactly. And that's really the core of our deep dive today. How Terrapower takes this material, this old U-233 byproduct, and refines it into a treatment using an incredibly rare isotope, Actinium-225.
Actinium-225.
Yeah. Terrapower isotopes, their division, is sort of the first crucial step in a chain that ends up with this product getting to patients through something called targeted alpha therapy.
Targeted alpha therapy? Sounds fancy. Break that down for us.
Sure. So the basic idea is using alpha radiation, which is essentially helium nuclei, 2 protons, 2 neutrons, to very precisely target and, well, destroy cancer cells.
Alpha radiation, I remember that from physics class. But hang on, if it's good at killing cells, why hasn't it been a major cancer treatment before now?
That's the key thing. Alpha particles pack a punch. They're great at damaging cells, but they have almost no range. They get stopped very, very easily, like by a sheet of paper or even just the outer layer of your skin.
Okay, so they can't penetrate deep into the body where tumors often are.
Exactly. That short range made them seem, well, impractical for traditional radiation approaches.
So what changed? What's the breakthrough?
It's really about new developments in pharmaceuticals. Scientists have gotten incredibly clever at designing molecules, specific molecules that act like little guided missiles. They seek out and bind only to cancer cells.
Okay. Targeted delivery.
Precisely. And the brilliant part is they can attach this Actinium-225 to those targeting molecules.
I see. So the molecule is the delivery truck, finds the cancer cell's address, and the Actinium-225 is the cargo that does the damage right there.
You got it. So you get this really focused damage right inside the tumor, but you minimize the harm to all the healthy tissue around it.
Which is a huge difference from, say, chemo, right? Which kind of hits everything.
A massive difference. Chemo affects rapidly dividing cells anywhere, hence the side effects. Even external radiation beams, while targeted, still have to pass through healthy tissue. This alpha therapy aims to avoid that collateral damage.
That sounds incredibly promising. Is there evidence it actually works that well?
Well, the source material we looked at shared a really striking example. A patient with metastatic prostate cancer. So, cancer that had spread quite widely.
Right, which is often very difficult to treat.
Very difficult.
Yeah.
This patient received Actinium-225 therapy, and the scans taken just a couple of months later showed, well, a remarkable improvement, a really dramatic reduction in the cancer.
Wow, just a couple of months. That's impressive. So this Actinium-225 is really the star player here. What makes it so special for this?
It has a few really ideal properties. As we said, it emits these high-energy alpha particles. But crucially, it does it over a super short distance. We're talking just a few cell diameters.
Okay, so really localized damage.
Extremely localized. It zaps the target cell, maybe its immediate neighbors, but doesn't go much further. Minimal damage to nearby healthy cells.
So does that translate into fewer side effects for the patient? The kind we usually associate with cancer treatment?
It seems so, yeah. Traditional radiotherapy or even other radiopharmaceuticals can mean isolation, significant side effects. But with Actinium-225, because the alpha particle stops so quickly within the body, the patient themselves doesn't pose a significant radiation risk to others.
Oh, that's interesting.
Yeah. So often patients can be near family. They might not need long hospital stays. They can often go home feeling relatively well without the severe hair loss or nausea because it's so targeted, right? It spares most of the body's other rapidly dividing cells.
That's a huge quality of life improvement. And what about for the doctors, the hospitals? Are there logistical benefits too?
There are, definitely. Actinium-225 has a half-life of about 10 days,
10 days.
which is kind of a sweet spot, logistically speaking. Some isotopes have half-lives of minutes or hours.
Right, meaning you basically have to make them right there at the hospital.
Exactly. You need expensive equipment, like cyclotrons, on site. But with a 10-day half-life, Terrapower isotopes can produce the Actinium-225, do quality control, and then ship it globally. It arrives at the hospital still potent enough to use.
So a much more reliable, consistent supply chain, especially if patients need multiple doses over time.
Precisely. It makes the whole process much more feasible for wider use.
10 days. Good time frame. I think I saw in the sources Terrapower has a nickname for this stuff.
You do, yeah. They call it their golden egg.
The golden egg.
Because it just has this perfect combination,
Yeah.
Potent alpha particles, that super short range for precision, and then this manageable half-life for logistics. It ticks all the boxes.
The golden egg. Nice. But, okay, here's the catch I remember reading about. The source material for this golden egg is ridiculously rare, right? Something about paper clips.
Yeah. That refers to the global supply of readily available thorium, which is one way to get to Actinium-225. It's incredibly scarce in the forms needed.
Less than 2 paper clips worth in the whole world. That sounds like, well, not enough.
It's extremely limited, and this actually loops back to that Cold War research again. Besides uranium-233, the U.S. was also looking at using thorium-232 to sort of breed nuclear fuel. And it turns out that process naturally creates an isotope called thorium-229,
Thorium-229.
which is the direct parent isotope of Actinium-225. Thorium-229 decays into Actinium-225.
Ah, so this stockpile of old uranium-233 waste has been doing something useful all this time.
Exactly. That stockpile, about 450 pounds of uranium-233, has been slowly decaying over the decades. And as it decays, it produces thorium-229. About 20 years ago, scientists started figuring out how to extract tiny amounts of this thorium-229. And that thorium-229 then naturally decays into the actinium-225 that cancer researchers got so excited about. But even so, the total amount of this extracted thorium-229 worldwide is still tiny. Less than 2 grams.
Less than 2 grams globally. Seriously, how can that possibly be enough to treat anyone?
And that is why Terrapower's move is so significant. They essentially got the rights through investing in the disposal company Isotech to process that entire uranium-233 stockpile at Oak Ridge.
The whole 450 pounds.
The whole thing, specifically to extract the thorium-229 that's built up inside it over all these years.
Wow. So they're mining this decades-old waste product for this incredibly rare ingredient, turning a liability into a huge asset.
That's exactly it.
How much thorium-229 do they think they can actually get out of it? Still sounds like it might be a small amount.
Well, relative to the starting material, it is small.
Yeah.
They estimate recovering maybe 40 to 45 grams of thorium-229.
45 grams. Okay, help me visualize that.
Think of like maybe 16 metal washers you'd get at a hardware store. Yeah, weight.
16 washers. Okay, my intuition is still screaming. That's tiny. How can that possibly make a difference for millions of cancer patients?
Right. It seems counterintuitive. But this is where the power of targeted therapy and nuclear physics comes in. That 40-45 grams of thorium-229 as it decays is projected to produce enough actinium-225 for millions of treatment doses.
Millions from 16 washers worth.
Millions. Potentially enough to treat patients for decades to come. Because you need such a minuscule amount per dose delivered right to the target.
That's mind-blowing. And to think the original plan was just to bury this stuff.
Yeah, the Department of Energy's plan was basically to mix the U-233 waste with grout and bury it permanently underground. One of Terrapower's own radiochemists called that plan a huge shame in retrospect.
I'll bet. Losing all that potential actinium-225.
Exactly, given what we know now about its medical value.
It really makes you think about what else we might be throwing away, doesn't it? Okay, you mentioned needing tiny amounts. The source used Avogadro's number to make a point here. Chemistry class is a distant memory. Remind me.
Yeah, Avogadro's number. It's just a way of counting atoms or molecules.
Yeah.
It's a huge number, like 6, followed by 23 zeros. It tells you how many atoms were in a mole of something. Standard chemistry amount.
Oh, a massive number.
Massive. And the point was, even in just 45 grams of thorium, there's an almost unimaginable number of atoms. So
Yes.
many that theoretically, if you could perfectly target every single resulting actinium-225 atom,
Yeah.
you'd have enough to deliver one atom to almost every single cell in every single person on Earth.
Get out. Seriously?
Seriously. Now, obviously, we can't target that precisely, but it shows the sheer scale we're talking about at the atomic level.
Mm.
The human body has maybe 10 trillion cells. So even delivering a small number of these potent alpha emitters directly to the few billion cancer cells, that can be incredibly effective. It highlights the power of that targeted delivery.
Okay, my mind is officially blown. But working with this stuff, even small amounts, it's still highly radioactive. How do they actually do it safely?
Safety is absolutely paramount. They use what are called hot cells. Think of super reinforced rooms with incredibly thick walls, often several feet of concrete, and leaded glass windows.
Okay, like a bunker.
Pretty much. And all the work inside, all the manipulation of the material is done remotely, using highly sophisticated robotic arms. The scientists are completely shielded.
So robots are handling the radioactive stuff, like in a sci-fi movie?
Kinda, yeah. Very precise, remotely operated robotic systems. No direct human contact with the potent material. And the chemistry itself requires insane precision because they are dealing with such tiny quantities of actinium at any given time.
How precise?
They talked about cleaning their glassware to remove trace metal contaminants down to parts per trillion.
Parts per trillion. That's hard to even comprehend.
It's an incredible level of purity they need to achieve.
And moving the material between steps, I remember reading something about Ghostbusters.
Yeah. They have these specialized containers and transfer systems. Beta canisters and alpha ports, they call them. They playfully nicknamed them Ghostbusters-like because they allow safe transfer of the radioactive material from, say, the hot cell to a glove box while maintaining complete containment and shielding.
Okay, a memorable image. But still, what about the people working there? Even with robots and shielded rooms, is there still a significant risk?
Well, the source material was pretty clear on this.
Yeah.
If everyone follows the very strict safety procedures, and these places have incredibly strict procedures, the actual radiation dose workers receive is quite low,
Low-like.
comparable to the background radiation exposure you get on a long airplane flight.
Oh, okay. That puts it in perspective. The shielding and protocols really work.
They're designed to. Decades of experience in the nuclear industry have gone into developing these safety measures.
Right. So could you walk us through the basic steps? How do they get from the U-233 calorium mix to the final vial of actinium-225?
Sure, it's a multi-stage chemical purification process. First, inside that heavily shielded hot cell, they do a kind of crude initial separation, getting the actinium fraction away from the bulk of the thorium and other decay products.
Okay, step one.
Then they reduce the volume, concentrate it, and do a final separation step. This removes more of the unwanted thorium and radium isotopes.
Getting cleaner.
Exactly. Then it's transferred using those Ghostbusters ports into something called a glove box. Still shielded, but allows for more hands-on, albeit indirect, manipulation for the final, superfine purification steps.
Final polish.
Right. After that, rigorous QC checks, quality control. They test for radiochemical purity, making sure it's the right chemical form, and radionuclidic purity, making sure it's purely actinium-225 without other radioactive isotopes sneaking in.
Gotta be perfect.
Absolutely. And then finally, an automated system fills the final product vials ready to be shipped out to the customers, the pharmaceutical companies, and researchers.
Wow. It's a complex chain. And this isn't just a plan, right? They are actually doing this now.
Yes. That's a key point from the sources. Terrapower is operational. They're running weekly production batches. They are actively shipping actinium-225 right now to companies conducting clinical trials for various cancers.
That's incredible. So it's moving from the lab bench through this complex process and actually getting to the places where it might help patients.
It is. It's happening.
It must be quite something for the people working there. Knowing what they're producing could have such a direct impact.
Absolutely. The source mentioned that sense of purpose is really strong within the team, knowing that the vial they just filled, within maybe a few weeks, could be administered to a seriously ill cancer patient in a clinical trial somewhere.
Yeah, that's powerful motivation. It really puts a human face on all this complex science and engineering.
It does. And, there was that little personal anecdote in the source material, too, about the visitor.
Oh, yeah. The radon gas incident.
Right. Despite all the shielding and procedures, they set off a detector, probably just from naturally occurring radon, which is radioactive,
Yeah.
and ended up creating their own tiny, tiny sample of low-level waste just from being there.
Little souvenir. A good reminder, though, of the invisible forces they're dealing with, even at background level.
Exactly, even when everything is incredibly safe and controlled.
So wrapping this up, it's a pretty amazing story. Terrapower takes this nuclear waste, this legacy material from the Cold War,
Extracts this incredibly rare isotope, Actinium-225,
using some seriously high-tech processes in shielded cells.
and delivers it for use in targeted alpha therapies that are showing real promise against tough cancers.
It really does feel like realizing some of that early, atoms for peace kind of potential, using nuclear science for something unambiguously good.
I think that's a fair way to put it. Transforming waste into medicine, and a powerful example of innovation, the grand potential of the atom, as you say.
It really makes you wonder, doesn't it, about the bigger picture. How many other things that we currently consider waste from maybe some other industry or some past era might actually hold incredible value?
That's a great point.
What other hidden resources are just waiting for the right technology or maybe just the right shift in perspective to unlock them? What other big problems might have solutions hiding in plain sight, maybe in things we've already written off?
That's definitely something to think about. The ingenuity required to see potential where others just saw a problem. It's
Yeah.
it's pretty inspiring.